30-ton machine hits a carrier deck at 180 miles per hour. In 2 seconds, it stops dead. No reverse thrust, no engine braking, just a steel cable strung across a flight deck, taking 900 pounds of force in a single violent snap. And that cable is the entire answer to one of aviation's most overlooked engineering puzzles. Commercial airliners use thrust reversers. Every wide-body jet you've ever boarded deploys clamshell doors or blocker panels the moment it touches down, redirecting engine exhaust forward to help scrub speed off the runway. It's standard, it's expected. Therefore, when people learn that fighter jets, aircraft costing over $100 million, built with every performance advantage modern engineering can produce, have no reverse gear at all, the assumption is that someone made a weight trade-off. That engineers looked at the numbers, decided reversers were too heavy, and left them off. That assumption is wrong. The real reason is more violent than a spreadsheet. A car engine reverses by flipping the direction of the crankshaft through a gearbox. The mechanical chain is clean and direct. The engine sends one way. The gearbox flips the output. The wheels roll backward. Simple. But a jet engine doesn't work like that. A jet engine produces thrust by accelerating a continuous column of air rearward. That's it. That's the whole mechanism. Air enters the front, gets squeezed and combusted and accelerated, exits the back fast, and the aircraft moves forward because Newton's third law doesn't negotiate. Reverse in a jet doesn't mean spinning the engine backward. It means physically redirecting that column of air so it exits forward instead of rearward. And the only way to do that is with doors, physical deflectors that catch the exhaust and bend it around. So if it's just doors, why not put them on a fighter? But here's where it gets crazy. A commercial airliner deploys its thrust reversers at the moment of touchdown, with engines running at idle or just above it. The aircraft is heavy, moving slowly compared to its cruise speed, and the aerodynamic environment is about as calm as it gets for a jet that size. The reversers open into relatively cool, low-pressure exhaust. The geometry works. But a fighter jet operates in a completely different world. When an F-16 or an FCA-18 is coming in hot, even on approach, engines throttled back but still running far hotter than a 737 at idle. The exhaust conditions are violent. The temperatures are higher, pressures are higher, the airframe is smaller and tighter, and the gap between the exhaust nozzle and the intake is measured in feet, not the length of a commercial fuselage. Deploy thrust reverser doors in that environment, and two things happen. First, doors themselves get shredded by exhaust temperatures that would melt conventional materials in seconds. Second, and this is the part that kills the idea entirely, the redirected exhaust doesn't just blow harmlessly forward. It curves back around the fuselage and gets pulled straight into the engine intake. The engine starts breathing its own hot, depleted, turbulent exhaust instead of clean ambient air. And when that happens, the engine does something called a compressor stall. This is the part everyone misses. A jet engine runs on a pressure gradient. The intake draws in air. The compressor, a series of spinning blades arranged in stages, each one squeezing the air harder than the last, builds pressure steadily from front to back. Then combustion fires. Then the turbine extracts energy to keep the compressor spinning. Then clean, high-velocity exhaust exits the back. The whole system depends on that pressure gradient staying intact. Clean air in, high pressure in the middle, exhaust out. Disrupt the gradient, and the compressor blades, which are angled precisely to bite into clean incoming air, suddenly find themselves trying to bite into hot, swirling, already depleted gas coming from the wrong direction. The blades stall. They stop generating pressure. The engine loses thrust almost instantly. A compressor stall doesn't just mean the engine gets quiet. Pilots describe it as a shotgun going off inside the aircraft, a physical concussive punch transmitted through the airframe. In mild cases, the engine surges and recovers. In severe cases, it flames out entirely. On a carrier approach at 150 miles per hour, with 300 feet of deck left and no altitude, a flamed-out engine isn't an inconvenience. It's a crash. Therefore, fighter jets don't have reverse gear. Not because engineers forgot or ran out of weight budget, but because the engine would actively fight back against any attempt to redirect its own exhaust. Now, commercial jets manage it because the physics are different in every important way. A Boeing 777 touches down at around 160 miles per hour, but weighs up to 700,000 pounds at landing. That's roughly the weight of 100 fully loaded school buses. It needs a long runway and every stopping aid it can get. Thrust reversers on that aircraft contribute maybe 15 to 20% of total stopping force. The rest comes from carbon brakes biting into wheel discs and spoilers killing lift. The reversers help, but they're not the main event. Remove them, and you need more runway. Keep them, and the geometry works because the engines are running cold, and the fuselage is long enough to separate intake from exhaust. A fighter jet lands light, fuel burned down, weapons expended, often weighing less than half what it took off at. The kinetic energy problem is smaller to begin with. Therefore, the stopping system looks completely different. An arrestor hook drops from the tail, catches a cable strung across the runway or flight deck, and transfers the aircraft's momentum into a hydraulic braking system buried in the ground or the ship. The wire does in 2 seconds what thrust reversers and brakes take 30 seconds to do on a 777. It's brutal, and it's precise, and it works exactly because it bypasses the engine entirely. Wait, drag chutes? That's a World War II technology. Why is it still on a $100 million aircraft? Because it works. The F-15 still uses a drag chute hand-packed by ground crew before every mission, a folded fabric deployed at touchdown to create enough aerodynamic drag to scrub speed without touching the engine or demanding runway length the base might not have. It's unchanged in concept from the chutes strung behind prop-driven aircraft in the 1940s. The physics of fabric catching air haven't improved because they don't need to. And not every fighter has a runway with an arrestor wire. On a forward operating base, a strip of concrete or packed dirt in a contested environment, the drag chute might be the only stopping system available. The Soviets tried a different approach. The Su-25 Frog Russian ground attack jet built for close air support at low speeds actually does have a thrust reverser. One of the very few combat aircraft that does, but the Su-25 operates at speeds and altitudes closer to a turboprop than a supersonic fighter, slower, lower, cooler. The exhaust environment is manageable. The geometry barely works. It's the exception that defines the rule, and even then, it's a narrow mechanical compromise built for a specific mission profile that no Western Air Force considered worth copying. Here's the surprise. In the early 1950s, engineers at de Havilland and Rolls-Royce were not sitting back assuming reverse thrust was impossible. They were actively testing thrust deflectors on early jet aircraft, the Vampire, the Meteor, trying to solve the same problem. At the Royal Aircraft Establishment in Farnborough in 1952, according to one version of testing records, a thrust deflector test on a Gloucester Meteor caused a compressor surge so violent it cracked the engine casing while the aircraft was still on the runway, not in the air. On the ground at relatively low power, the deflected exhaust came back around and hit the intake hard enough to split metal. The test program didn't survive that result. Meanwhile, the U.S. Navy, which had been landing propeller aircraft on carriers since the 1920s, was watching the first generation of jet aircraft arrive on its flight decks and realizing that the arrestor hook, which had always been a backup system, was about to become the primary stopping method for every aircraft it operated. Jets land faster. Jets have no propeller drag to slow them down on approach. Jets, by their fundamental nature, cannot reverse. Therefore, the wire had to get stronger. By the time the F-4 Phantom entered service, the arresting cables on carrier decks were engineered to stop a 50,000-pound aircraft traveling at 150 miles per hour in under 300 feet. The peak tension in that wire during a trap reached 900,000 pounds, briefly making the arresting cable the single most stressed piece of equipment on the entire ship. That's more force than a suspension bridge cable carries at midspan, and it happens dozens of times a day. Every day the carrier is at sea. The wire gets replaced after roughly 100 traps, not because it breaks, because the crystal structure of the steel, the microscopic grain alignment that gives the cable its strength, has been stressed so many times that metallurgists consider it compromised. It looks fine, it tests fine, but the accumulated stress has changed what the metal is at a molecular level, and at 900,000 pounds of peak load, a compromised cable is a cable that will eventually fail without warning. Therefore, it gets swapped before that point, every time. If the wire snaps, and they do snap, anyone standing within the snap radius, which can be 50 feet or more, is in serious danger. Carriers have strict exclusion zones around arresting wires during flight operations. Sailors have been killed by failed cables. The wire is not passive safety equipment. It is a controlled detonation of mechanical energy happening on a floating runway. Everyone near it knows it. The no-reverse constraint has been silently shaping aviation around you for decades. Every commercial airport on Earth is laid out, assuming jets cannot taxi backward. Gates angle forward. Taxiways run in one direction. The pushback tug, a squat, dense machine that can weigh 100,000 pounds, exists for the sole purpose of moving jets away from gates because the aircraft cannot do it themselves. Airports spend hundreds of millions of dollars on pushback fleets and the logistics to run them, to solve a problem that originates in a geometry inside the engine no bigger than a dining room table. Drag chute compartments on aircraft like the F-15 are still packed by hand, by a human being, before every single sortie. The ritual is identical to what ground crews did in Korea. The technology has not changed because the physics have not changed. The foam-covered barrier net at the end of a carrier flight deck, the last resort for a jet that misses all 4 wires, deploys in under 3 seconds and stops a 20-ton aircraft without killing the pilot. The net is designed to absorb the aircraft, not block it. It gives way progressively. It's an engineering solution that exists entirely because there is no reverse option. When an FC-18 misses all 4 wires on a carrier, called a bolter, the pilot must go to full afterburner the instant the hook clears the last wire, not shortly after, instantly, because the aircraft is now running out of flight deck with no stopping option and no reverse, and the only survivable outcome is to fly. The pilot doesn't get a moment to decide. The throttle goes forward whether they're ready or not. The F-35B's vertical landing mode is the closest any fighter has come to solving the reverse problem without solving it. By redirecting engine thrust downward through a lift fan, the aircraft can descend vertically onto a small pad with no forward speed, functionally replacing the need to taxi backward. But it's not reverse thrust. It's the reverse of forward motion achieved through vertical force. The distinction matters because the compressor stall problem still exists. The engine still cannot breathe its own exhaust. The solution works around the constraint rather than through it. But the system was so mechanically complex, 4 nozzles that had to move in sync, each with its own set of controls and backups, that the aircraft had redundant nozzle control systems specifically because a single failure in flight was potentially fatal. The complexity was the cost of approximating reverse thrust. On short forward operating bases in combat zones, fighter pilots sometimes land using a temporary arresting cable strung across a dirt strip, the same concept as a carrier, implemented with field equipment and a prayer. Because without reverse, the wire is always the answer. The Concorde is the last major example. Its Olympus engines used thrust reversers, but only below 60 miles per hour at strict power limits, under specific conditions that engineers spent years defining precisely to prevent exhaust re-ingestion. Every limitation on the Concorde's reverser maps directly onto the geometry problem that kills the idea for fighters. The Concorde made it work by accepting massive constraints. Fighters don't have the runway length or the low-speed environment that makes those constraints survivable. But here's where it gets crazy. In the other direction, modern carbon brakes on aircraft like the F-22 are so effective that on a full-length runway, the no-reverse problem is almost academic. The brakes can generate more stopping force than the airframe can safely absorb. The limiting factor isn't braking power, it's tire friction and structural load limits. On a long runway with good brakes and a working drag chute, the fighter stops. The reverse gear question doesn't come up. The unsolved problem is the short, damaged, improvised strip in a contested environment where the drag chute is torn, the wire isn't installed, and the runway ends in 2,000 feet of broken concrete. That's the real gap. DARPA's STOL program, Extreme Short Takeoff and Landing, is exploring thrust vectoring combined with active flow control to let combat jets land in under 500 feet without reverse thrust and without a wire. No reverser. Same outcome achieved through different physics. Adding thrust reversers to a stealthy aircraft like the F-22 would require external doors that break the smooth fuselage geometry responsible for its radar cross-section reduction. The Air Force has explicitly studied and rejected this. A reverser door is a corner reflector, exactly the shape stealth engineers spend careers eliminating. Therefore, the F-22 will never have one, regardless of what advances in high-temperature materials might someday make the exhaust environment manageable. So, reverse gear didn't fail the fighter jet. The fighter jet outgrew the question entirely. The geometry of a jet engine is a one-way commitment. Air in, thrust out. Bend it, vector it, redirect it through a lift fan or a rotating nozzle, but reverse the direction of a controlled explosion inside a machine designed around a precise pressure gradient, and the machine fights back. That 900-pound arresting cable, replaced every 100 traps because stress changes steel at the molecular level, is the physical answer to an engineering problem that could not be solved inside the engine itself. They didn't forget to add reverse. They built something better out of wire, mathematics, and the precise knowledge of exactly how much punishment steel can take.